তুমি সৌমেন্দ্র দাস কথা বলে টাইমটা জানিয়ে দাও। ডিম খাই মানে জমে গেলে খান ওই তো হ্যাঁ সৌমেন্দ্র হচ্ছে নাম্বার অফ পাওয়ার উপরে নির্ভর মানুষ খায় হ্যাঁ মানুষ খায় ভাত খায় না আবার মানে ক্যাটারপিলার খায় না বেশি পা আরশোলা খায় না চিড়ে খায় না মানুষ হামাগুড়ি দিলে খায় না মানুষ একজনের প্রাইম প্রাইমের প্রাইম প্রাইমের মধ্যে প্রাইম নেই কথাটা আছে WhatsApp হোয়াটসঅ্যাপে গিয়ে তো জানি তো yes, it changes the so you while the random goes, if the graph changes, there is a different so what is
in the sequel of Professor Ashok with memorial lecture, today again we'll have Professor Pietro Caputo from University Roma State, and his talk would be on functional inequalities in random permutation dynamics, spectral graphs, and entropy factorizations. Let's welcome Professor Pietro.
Thank you very much for inviting me to speak at this colloquium. And thanks again for inviting me to the Ashok Maitra Memorial Lecture. It's really a pleasure to be here. So I will talk about functional inequalities for random permutations and mostly focusing on spectral gaps and entropy factorization. This is part of some ongoing work that we have started several years ago, and the plan of the talk will be as follows. Namely, I will first introduce what we mean by transposition shuffles, also called interchange process, and for these we will have quite a good understanding of the spectral gap problem. Then we will try to generalize this to shuffles, where you don't exchange just two elements at a time, but you exchange a whole block, a whole set of elements at every time. And for this, we will have some open problems, and I will state a spectral gap conjecture. And then the second part of the talk will be about some entropy versions of the spectral gap problem. Spectral gap is a problem about eigenvalues, or the first non-trivial eigenvalue of the process. And entropy analog is essentially a functional inequality that you get when you replace the variance functional with an entropy function. Because the eigenvalue problem can be stated in terms of a variance, functional inequality for the variance. And instead, here we will look at functional inequalities for the entropy, namely relative entropy. So we will look at relative entropy inequalities. And you will see that there will be many open problems here. The problem with entropy is much more challenging, and we will be able to state some results in an homogeneous setting that I will call the mean field setting. And already this gives some interesting application to a combinatorial problem allowing to prove a long-standing conjecture about upper bounds on the permanent of an arbitrary matrix. So this, I put here just a few references about some previous work we did with Liggett and Richthammer in 2010, and some more recent papers we have on this with Alexandre Bristiel and Justin Salès. And you can find all the relevant references within this work, in case you're interested. About the literature. So let me start with the interchange process or transposition shuffle. So the game here is to consider a permutation, which so we consider Sn's the set of permutation, and we take the uniform distribution over permutation. Okay, so n is going to be something that you can think of large, but it's going to be finite. And we will not necessarily think of n going to infinity. N is fixed, is a finite. Okay, then we can think of the process as a process with a state space Sn, namely the set of permutation. And the way you can think of this is as the configuration of n cards in a deck of cards, or you can think of that as n labeled particles occupying n given positions in such a way that each particle occupies exactly one position. Okay, this is a convenient picture because then we will try to follow just one particle or two particles at once. The interchange process is defined as follows. Suppose you are given some rates cxy, where xy is an unordered pair of vertices. And for each cxy, for each unordered pair, you have some weight, something non-negative, cxy. It's arbitrary for the moment. And then you look at the continuous time Markov chain that is obtained by the following infinitesimal generator. If you look at the function f on the permutations, then the generator L applied to f gives a new function that computed on the permutation eta is given by this expression. So the way to read this expression is as a weighted sum with the weights given by the rates cxy, and then you have a gradient here. And the gradient is computed when you swap the labels at x and y. So your permutation is given eta, and then at vertex x and vertex y, you swap the two elements. So this is like exchanging the position of the two particles that occupy this. And a more concrete way to represent this process is by attaching to every pair, to every unordered pair, a Poisson process, independent Poisson process for every pair, and the Poisson processes have rate cxy. And when a pair rings, you swap the labels there. So this is exactly the expression you get for the continuous time Markov chain in this case. So think of a process where at these random times given by this Poisson process, you swap the labels. It's called the interchange process. And let's back here. So we're interested in a spectral gap, namely, if you observe that the infinitesimal generator is actually a self-adjoint operator in L2 with the uniform distribution, then it's actually a finite matrix, because here the state space is finite, the 10 factorial dimensions. So you will have n factorial eigenvalues, and it's not difficult to see that they will all be negative or at most 0. So you can parameterize them by minus lambda I, and lambda 0 would be the 0 eigenvalue, which is always there associated to a constant function. And then you can look at the next eigenvalue, lambda 1, and then you order them in such a way that the last one is lambda n factorial. Now, it's not difficult to see that lambda 1 will be positive if and only if the rates define an irreducible structure. A reducible structure means that if you look at only the weights that are strictly positive, this gives you a skeleton associated to the weights, or if you prefer, it's a graph where the weights
This one
are positive.
What's the transition here? You said the x belongs to, what's the transition? For Markov chain, what is the transition from where to where?
Okay, the transition is from eta to eta xy.
So
Eta xy is the swap.
swap transition.
Yes.
Only for particular particle or any some of the all particles?
You sum over all unordered pairs. So you have your particles arranged in some order, and then you pick two positions, x and y, and you swap the particle which sit at x with the particle which sits at y. So this is exchanging the position. Yeah. What is?
They want to swing.
Oh, sorry. This box n is all the integers from 1 to n. Sorry. No problem. So I'm looking at permutations of all these indices. I look at them as vertices where I put my particles. Any other question? So it's clear what the process is, and it's a Markov chain with an infinitesimal generator L. This defines a non-positive definite operator, or if you want, it's just a matrix here. And everything is finite dimensional, so you can just consider the spectrum, and you will have a positive eigenvalue lambda 1, if and only if there is an irreducible process. And this process is irreducible as soon as, or if and only if the CXY have a skeleton that is irreducible. Okay. This allows you to go from any configuration to any other. So
Can you just give me one?
So one thing that we are going to use is that lambda 1, being an eigenvalue of the self-adjoint operator, is characterized by a variational principle. And the variational principle is given in this way. So you have the infimum over all functions f, which have a variance different from 0. And you have the ratio between the Dirichlet form and the variance, where I'm using this notation here. The variance is just the standard variance of a function f under the uniform distribution mu. And the Dirichlet form is classical object in continuous time Markov chain, is written as minus mu minus the average according to mu of the product f times Lg. This is dfg. And here I'm taking dff. It's a quadratic form. It's basically just the scalar product of f with Lf at the numerator. And in the denominator, you have the variance of f. This is the classical variational principle for the smallest eigenvalue. I'm I'm using variance in the denominator because I don't want the eigenvalue 0. So I'm going to get functions that are orthogonal to the constant function. Okay, so classical facts about spectral theory is that the eigenvalue lambda 1 governs the decay to equilibrium in L2 norm. So if you decompose the exponential of t times L applied to F, you will see this formula immediately, because when you decompose this in the normal basis of eigenfunction, you will see that the first term cancels exactly the expected value of F according to mu. This is the projection, orthogonal projection to constant functions. And then the rest of the terms are bounded in this way. E minus lambda 1, because lambda 1 is the worst possible rate of decay. And then you have the L2 norm of F minus mu. So this is an important quantity for convergence to equilibrium. And one way to see this is by this type of. Actually, the inequality is equivalent to this in the sense that if this has to hold for a constant here, lambda 1 for all F, then this constant must be this one. Okay, this is classical thing. For a bit of notation we need is the following. Let's introduce this notation fxy for the function evaluated at the swap configuration. And let's use this observation, namely, when we symmetrize, when we use the symmetry of the operator L, we can show that by putting 1/2 here, we can rewrite the Dirichlet form in this form with two gradients. So I have a gradient of F and a gradient of G. This is also classical. And forgive me for using notation Blackboard E for the same expectation under mu. So I'm going to use both notation. It's the same thing. It's the same thing as mu here. Now, if you introduce this object that I'm calling covariance xy fg, it's just by definition this quantity here, 1/4 the gradient of f and the gradient of g. Then I can rewrite the Dirichlet form in this form, as we have just seen that. And in particular, I can write the Dirichlet form when f equals g in this form here, where I'm using the covariance of f and f, which is actually a variance. Why do I call it variance? This is simple because think of this, if all of the particles are fixed except at x and y, so if everything is frozen except at x and y, then the variance would be a variance of a two-valued random variable, because either I keep the particles at x and y or I swap them. Because this is a uniform measure. If I freeze everything, so conditional on everything except x and y, the variance would be just this object. So the way to interpret this object is as a local variance when everything is frozen outside of x and y. This will be useful for what I will say later. So the interesting thing now is that this lambda 1 is characterized as a ratio of a weighted sum of local variances with the global variance. So one way to attack the problem of understanding this lambda 1 is by thinking of how can I decompose the global variance into a weighted sum of local variances. There is a worst case here, which will be the eigenfunction of the lambda 1, And in that case, the constant between the two things is exactly the lambda. So that's the point of view that I want to use here. Okay, so that's the functional inequality for spectral gap. Now let's see, because this is a complicated problem because you have n factorial dimension. It can be really difficult to attack. Of course, if n is small, you can try to do precise things. But here we also have the cxy is arbitrary. So we want to understand something that something about this lambda one. But one thing you can start doing is a much simpler process, namely follow just one particle. So take, say, particle labeled 1. This will be somewhere in your set of positions. And what is not difficult to see is that if you just follow that and forget about all the others, this will do a random move. But what else can it do? It can only jump from site X to site Y, and with rate exactly CXY. And vice versa. It can jump from Y to X with rate CXY. So this is the expression you get for the continuous time Markov chain that is obtained by just looking at one label. And let's call it L random walk. This is again is a symmetric matrix with eigenvalues minus lambda I, different from the previous one. And in fact, there's only n of them here because this is an n-dimensional problem. And there will be a zero eigenvalue, of course, but then there will be a lambda 1, and this lambda 1 will be positive if and only if the skeleton is irreducible. Okay? Is it clear, the random walk process? So in some sense, this random walk process is embedded in the bigger process we have looked at before. And this embedding provides immediately an embedding of the spectrum. Because the spectrum of the random walk must be a subset of the spectrum of the interchange process. This is just because if you give me an eigenfunction of the random walk, I can lift it to an eigenfunction of the interchange process just by looking at the position of one label, ignoring all the other labels. And this gives an upper bound on our spectral gap. So the lambda 1 of the interchange process is lambda 1 IP associated to our rates C is always upper bounded by the lambda 1 of the random walk associated to the rates. It's simple, because it's the worst eigenvalue. So it has to be at most this one. So the interesting thing is that we could prove that it's actually the same for any choice of C. This is a remarkable property of these interchange processes, because it allows you to say that the worst possible mode of relaxation is actually attained on a much simpler process, namely a process where you only follow just one particle. And this was a conjecture of David Aldous in the early 90s, and there were previous results on trees and on some other special cases in a series of papers. But then with Liggett and Richthammer, we were able to prove it for arbitrary weights and arbitrary structures. And there is some interesting structure coming out in the proof, because one has to develop some recursive strategy here, because the result is very simple if you only have two vertices. It's actually obvious if you have two vertices, because then if you just follow one of the two labels, then it's the same as following the two of them. Constraint. So if you're able to develop a strategy that brings you from arbitrary n to something that is n equals 2, then you're done. But that required some new ideas. And the main idea here was that the strategy to go from n to n minus 1 was to eliminate a node, but not just eliminating the node of the network. Here you can think of a network where every edge has a weight CXY. The edge XY has a weight CXY. So if you want to eliminate node X, then you're eliminating all the edges that come that involve X. And one strategy to eliminate the node X is to cancel all the weights that involve X and redistribute the weights in the remaining vertices in such a way that you preserve an equivalent electric network. This is a concept that is familiar from electric network analysis, and it's essentially there is a way to redistribute weights so that the potential will be the same as in the previous setting. But I will not go into the details here. And we found that this was actually a good strategy, because once you do this, then you have to make the proof, then you have to implement several steps, but the key tricky part will be prove a certain inequality between Dirichlet forms, comparison inequality between Dirichlet forms from the interchange on G and the interchange on the reduced graph GX. Okay, this is very tricky. I will not talk about this, but it's just to give you an idea of what has to be done to do this kind of. And essentially, this ends the story for interchange processes, because then you have reduced the problem to computing spectral gaps of a much simpler process, which is the random walk, and for that you may have tools to analyze this, or of course it will depend on the structure of the waves, and there's not much more you can say in general. But this is a strong reduction of the complexity of it. Okay, so then I want to talk about block shuffles, which is a generalization of this interchange process. So what we're going to do is, instead of exchanging the position of two particles, we want to reshuffle the positions of an arbitrary set of particles. Yeah.
So the simplex is then it only depends on x, y, where x is fixed, right? So only a part of the.
Okay, so that's a good point. In the recursive strategy, you are choosing some node x, but actually you can choose any node x. It doesn't really matter. So you're given your n vertices. Pick anyone, just pick the first one, and remove that with the strategy of redistributing. Then you get an inequality, and then you get to remove another one, and then you get down to two. But in order to be able to make sense of that, you need this comparison inequalities, which are very delicate.
So my question is then, when you're talking about the spectral gap of the reduced process,
yes,
are you picking one node at random and following the
No, you can just pick, always say the first.
Always say the first.
Or the last. You can always, the strategy will work whatever sequence of nodes you pick in the recursion.
But shouldn't the spectral gap depend on the weights?
It will depend, but you get a sequence of inequalities. They are always nested in such a way that everything
works out.
Yeah. It will depend. But I'm happy to discuss the proof later on if you want. Just there is not so much time to get into it. So let's go to block shuffle, where I want to reshuffle a block. So think of them as cards, maybe. And when a block A rings, A is a subset of vertices here, and it will ring with some rate alpha A. When a block A rings, I take all the cards there and reshuffle them completely. Like put them in a uniform configuration in those positions. So another way to stay in this is that when the block A rings, I freeze everything outside of the block A. And within A, I take a sample, a perfect sample from the equilibrium distribution conditioned on the outside configuration. And I call mu of A this equilibrium distribution condition on the outside configuration. So this mu of A applied to F is conditional expectation of F given the outside configuration. Eta A complement means the particles that's the position of the particles on the sides indexed by A complement. Is this clear? I have a block A that rings, and on that one I reshuffle completely, but outside everything is frozen. This is the measure mu A. So one way to write the infinitesimal generator of this dynamic is this one. With rate alpha A, I reshuffle completely the particles in A, and notice that when A has cardinality 2, what you do by reshuffling is either you keep those positions or you swap them. So if you restrict to A's that have cardinality 2, we are back to the previous process, except that there is a factor of half of laziness here, because you may stay in the current configuration with probability a half, or you may swap with probability. So I just want to convince you that this is a generalization of the previous problem, which corresponds to taking A only made of 2 vertices. Does that make sense? Okay, so again, I can think of this as an operator which will be self-adjoint. It's again symmetric, actually. It's not difficult to see that it's a symmetric, non-positive definite operator again, and you can again talk about the spectrum, and this will be the eigenvalues. And again, lambda 1 will be positive if and only if the alpha A's have an irreducible skeleton. What does it mean? It means that if you take only the blocks which have positive weights, discard all those which have 0 weight, then this gives you a hypergraph, because now it's hyperedges instead of edges like before. And this hypergraph is irreducible in the sense that, again, by navigating within the hyperedges, you can always travel from any point to any other. Okay. This is the definition of the block shuffle. And again, we can rewrite the Dirichlet form as a weighted sum of local variances. This is important, and that's why I introduced that type of notation, because I want to look at this Dirichlet form as a weighted sum of local variances. And notice that when alpha A is equal to 2 times Cxy for A equal to Cxy, so if A is binary, A has 2 elements, and I take alpha A equal to 2 something that I call Cxy, then we are back to the interchange process, because it's exactly the Dirichlet form we had before. So that's the factor 2 I was mentioning that takes into account the laziness. Okay. So this problem contains the previous problem, and it is reduced to the previous problem when you put all the weights to 0 if the cardinality is bigger than 2, and you keep some non-negative weights 2 times Cxy and when the cardinality is. So now the question is, what is lambda 1 in this case? What would you guess? Okay, there is one step that you can take, which is the same as the step that we took before, namely that you can look at the random walk. Here I've drawn some possible skeleton of the alphas, just something in mind. So you could try to follow just one label, okay, one particle. So suppose you just follow particle 1. What is going to happen? Well, it has to do a random walk. because it will jump to some place that is contained in some block, and then it will jump to some other place that is contained in another block, and so on. So if you do the computation, it's very simple. You see that it actually follows a random walk with some binary rates that are given by this expression here. This is quite obvious to understand because you have to, if you want to go from X to Y, you have to sum over all possible blocks A that contain both, and then you have to use that block. But the probability to actually end up at the target site is 1 over cardinality of A because of the uniformity. So this is simple manipulation. And again, you have this embedding. Because again, the random walk process is a sub-process of the big block shuffle. And so it's obvious, again, that the lambda 1 of the block shuffle associated to these weights alpha is at most the lambda 1 of the random walk associated to these weights C alpha that I've given. This must be always the case, whatever the alpha. So here the logic is I take an arbitrary alpha, this gives me some C alpha, and then I have this obvious comparison. But I made around the time we proved the interchange process conjecture, I formulated this much more general conjecture, saying that for any alpha, this should be the case. So it's not only, of course, if alphas are binary, this is equivalent to the interchange. But this is just about any alpha. So it's a very, very general structural algebraic property, if you want, about this type of process. And I formulated this conjecture about 15 years ago, but there is still no proof of this result. And there is strong evidence that it should be true, but there is no proof. And let me say that there are some partial results about this. And but before that, one way to understand this result is that when you compare the global variance of a function to a weighted sum according to alpha of local variances, what you get is the worst constant that you get in that comparison should be given by the random walk. So this is the way I interpret this as a functional inequality for the variance functional. And so it should be some sort of a property of the composition of the variance functional into weighted sums of local version of the variance function. That's a way I like to think about it. Let me say something about some partial results. It's quite simple to see. I observed this a long time ago that there are actually certain skeleton structures that are for which you can prove it's not too difficult to prove the result. And these are structures that can be reduced by eliminating nodes which have degree 1. So suppose, for instance, this node here, this has degree 1 because it belongs only to one block. So you can eliminate that. If you eliminate all nodes that have degree 1 in whatever sequence, and you end up with a binary skeleton, then you know that the result is here. So this is not difficult. There are more sophisticated special cases that were obtained in a recent paper of Alon, Kozma, and Puder, where they have a criterion under which this result will be true. And the criterion is basically that all hyperedges share a common core. And then what's left outside of this core is a binary structure. So that's a more sophisticated special class of special cases. Something that we were able to prove recently with Alexandre Bristiel is that actually the conjecture is true if the weights alpha depend only on the cardinality of alpha. So this is something we refer to as the mean field case. because it's a homogeneous, so you lose all the structure. It's only about cardinality. So it's like a complete hypergraph type of problem. But no matter what the function g is, you can prove this. Okay. Another thing that is kind of intriguing is that you could think that there is a bigger comparison here going on about eigenvalues, but actually it goes in the wrong direction. Namely, if you think of the eigenvalues of the block shuffle with weights alpha, then these are all one by one. They can be ordered in such a way that they are one by one dominated by the eigenvalues of the interchange corresponding to the binary version of the weights. So given the alpha, there is a binary version that's the alpha. And you can actually show, it's not so difficult, that these are all dominated. So they really sit below the spectrum of the interchange. So you're really trying to prove that despite this domination, the lowest one is actually, that's the claim.
Do you mean to say there exists a C alpha, or do you mean to, or C alpha is already defined?
C alpha is defined by this relation here. It's defined by the random walk. This one.
Yes.
Okay, so do you have any other question about this? So this is an open problem. It's also interesting to note that if you try to develop some recursive strategy that has a strict analogy with the recursive strategy we have developed for the interchange, you will immediately run into some difficult counterexamples, and it's quite delicate. You can't follow too much that type of analogy. Although it's reasonable to hope that there should be a recursive strategy, but to find that may be difficult. Okay, so now we have understood these problems in terms of domination of the variance functional, in terms of local variances, and we want to understand the entropic analogs of this and see what this gives us. Okay. So let's first define the entropy functional. So given a non-negative function f, I call the entropy of f the expected value of f times the log of f over mu f. This is the expected value here. And the key thing to keep in mind is that this entropy functional is the same as the relative entropy, or KL divergence. Namely, if you take a function f that is a probability density with respect to mu, that is expected value of f is 1, then the entropy of f is simply the relative entropy of the new probability f mu with respect to mu. This is just definition of relative entropy, gives you this. Now, instead of the variance of f, we will consider the entropy of f. And you will see where this, why this could be interesting. First of all, we need a local version of the variance, of the entropy, just like we had the local version of the variance. And the natural thing to do is just to compute the relative entropy with respect to mu a. Mu a, remember, is the conditional distribution obtained by freezing the configuration outside of A. A is arbitrary here. So for any A, you can define this local entropy, which is now given by this expression. Okay, so this can be seen as the relative entropy with respect to mu A. But this quantity depends on what you have outside of A, because it's conditional distribution given the configuration outside of A. So you may want to take expected value with respect to what is outside of A. And if you take expected value, you have these relations, and you, by adding and subtracting the log of mu AF, you immediately see this relation. This is a useful relation. You're probably familiar with this type of relation for variance. You have this formula for conditional variance, and this is the same formula for conditional entropy. Okay, good. So we have seen that the spectral gap for block shuffle with weights alpha was an inequality of this form. Remember, the variational principle had the Dirichlet form here at the numerator and had the variance at the denominator. So when you try to prove bounds on the spectral gap, what you're trying to prove is essentially this inequality. So you want to find the best lambda alpha that you can put here such that this holds for all functions f. This was the spectral gap. Now we do the same for entropy. And we call this inequality entropy factorization with constant gamma alpha. Namely, you want the best constant gamma alpha that you can put in this inequality so that it holds for all functions f that are non-negative. Entropy is defined only for non-negative. You can also take f which have mean 1 if you want. It's not restricted because this inequality is homogeneous of degree 1. So you can always multiply f by fixed constant. If you want, you can just work with probability measures with respect to probability density. Okay, so that's the problem now we want to understand. And there's a first obvious relation that you can observe, namely that this gamma should always be at most this lambda. For a fixed choice of alpha, it's always bounded above by lambda. The reason is that you can take f to be very close to 1. Namely, you linearize the entropy. And if you linearize the entropy, you obtain the variance. This is classical property. And if you do this linearization, basically, it says that if you satisfy this inequality, then you have to satisfy also this. So this is always upper bounded by. That's easy. There's also another observation that is quite interesting, and is that if mu were a product measure, which is of course not the case for permutation, but suppose for a moment that you had independent particles, and then what you could say is that this gamma is equal to the lambda, and it's equal to the minimum covering probability for a single side. This is the covering probability if you want. Let's think of alpha as a probability. This is not a restriction because you can always multiply alpha by a constant, so you can assume that the sum over alpha A is 1. So think of this as a probability, and then this alpha star is the probability, the minimum probability that you cover a single side by this process. And this is known as shear inequality in the case of product measures. It's actually known in the case of Shannon entropy, but when you have a product measure, you can easily relate the relative entropy to Shannon entropy. And then using Shannon entropy, shear inequality for Shannon, you can see this relation here for product. So in some sense, trying to compute this gamma alpha is saying something about how far from a product measure you are. Because if you were a product measure, you could just stick in this gamma alpha equal to alpha star. But here you will not be able to do that. You will have to do something slightly smaller. Because you will not be able to satisfy this with alpha star. Because the permutations are not a product measure. Because obviously, if I tell you that particle 1 is in vertex 1, there cannot be any other particle in vertex 1. So there's some constraint. On the other hand, the correlation between particle 1 and particle 2 is very weak, very close to infinity. So you expect that when n is large, this guy could be actually not too bad. So that's what we're trying to understand. Is it clear, the problem? Do you have any question? So we're trying to understand what is the best way to factorize the relative entropy functional given a set of weights alpha A. Ideally, we would like to understand this for any alpha A, but of course, this is going to be very difficult, but maybe we can try to say something for certain sets of alpha A. And that's what I want to talk about next. Before doing that, you could ask, why is this interesting? So what do we care? Why do we care about this? Well, I hope I convinced you that the variance inequality is interesting because it's a spectral gap problem and it has relations to decay to equilibrium and so on. On the other hand, it's not immediate from this. What are the relations to the random process? Or are there any other interesting implication of this? And let me give you a couple of motivation here. So why studying this gamma alpha? Well, the first observation, I'm not going to go into all details here, but the first observation is that if you understand gamma alpha, then you have a lower bound on the exponential decay to equilibrium in relative entropy. This inequality here is telling you that the relative entropy along the interchange, along the block shuffle, this is now the block shuffle with rates alpha, has this exponential decay with some constant rho. And some simple manipulations show that actually this rho is always at least this gamma alpha. So if you get a bound on gamma alpha, then you also have a bound on exponential decay. This is good motivation because you having exponential decay for Markov chains for the relative entropy in Markov chains is very useful to obtain mixing time bound. It's actually better than the spectral gap. Gives you much more mileage when you try to prove mixing time bound than what you get from spectral gap. It's actually very interesting to obtain bounds on this rho. And if you control gamma, then you control rho. That's an interesting, that's a good motivation. Let me give you some other motivation. Other motivation comes from analysis. Namely, this gamma can be interpreted as a subadditivity constant. Because when you write the inequality between the entropies, like we wrote before, then you can write this as a subadditivity. And this subadditivity is known to be equivalent to so-called Braskamp-Leib inequalities. And this is a whole family of inequalities that have been studied in great detail in various contexts, especially for probability measures on Euclidean spaces. But you can actually also be interested in studying these in the setting of permutation. It's actually an interesting problem, and I will show you an application of this with a permanent bound that I will give you in a minute. So why subadditivity? Let me just quickly go through this. Remember that we had this identity here for the conditional variances. And remember that this quantity is the one that appears in our factorization inequality. So if you write things in terms of this expression, then the factorization inequality is equivalent to this quantity. It's just an obvious manipulation here. And let's assume again that the alphas are probability. Then you get this can be interpreted as a subadditivity because you're computing a sum of entropies of conditional expectations and you compare it to the full entropy. This is usually called a subadditivity. And subadditivity by Legendre duality is known to be equivalent to Braskamp-Leib inequalities, which take this form. Braskamp-Leib inequalities is an inequality which tells you how well you can factorize a measure. Well known, of course, that when you have a product measure, you can take expectation of product is equal to product of expectations, but you would like to say something about how well you can factorize by putting some exponents here when you have a non-product measure. This is exactly answered by Braskamp-Leib inequality, of which Young inequalities and Cauchy-Schwarz and all that are all special cases. So this is a general way of encoding dependencies for a measure. And this inequality is equivalent to this. So actually, this is a good motivation for studying our factorization because it really is equivalent to the Braskamp-Cribb inequalities, which has many, many applications in analysis. The equivalence between the two was observed several years ago by Eric Carlin and Maitra. Okay, so now let me tell you something about this gamma alpha. And as I anticipated, so far we are only able to say something really interesting when alpha is homogeneous, namely mean field cases. So I'm assuming that alpha A is a function G of the cardinality of A, arbitrary non-negative function G of the cardinality of A. And actually, to make things simpler, just think that alpha is a constant over all sets which have a fixed cardinality, say L. From this result, you can get the general. So the interesting part is this. Suppose now you take alpha, which is constant, and the constant has to be 1 over n choose L, so that it is a probability. But it's just a convention. But the important thing is that this is non-zero only when A has cardinality L. So you take all sets of cardinality L, and you study the sum of the local entropies, and you want to understand how this is related to the global entropy. And it turns out that in this case, you can compute exactly the gamma alpha. And it's equal to log L factorial over log n factorial. And this inequality is saturated uniquely at multiples of a Dirac mass. So if you plug in F equal to a Dirac mass, then you get this with equal sign. And for any other function F, you get strict inequality. So there is a complete understanding of what goes on in this homogeneous case. And it's quite interesting because people had tried, remember that this inequality implies exponential decay of relative entropy. And it's interesting that people had tried in the past quite hard to get control of this exponential decay for this type of dynamics. Actually, for interchange process. Here, it's more general because it's block shuffle. So interchange would be L equal 2. It's interesting that in these papers by Li Yao, by Goel, Gao Postel, and so on, they studied the problem of exponential decay of the relative entropy, and they could get bounds on the constant. Whereas here, you can actually compute it. So in some sense, the problem for the exponential decay is usually called modified log-Sobolev inequality, if you're familiar with it, but it doesn't matter. It's also, you can also study the actual log-Sobolev inequality, but in both cases, you cannot compute the constant. You can just get a bound. And what is interesting is that the factorization estimate actually allows the exact computation of the constant. So this, to me, says that this entropy factorization inequalities is in many ways more natural or more flexible than actual modified log-Sobolev. So what can you do with these results? Let me give you very quickly this application to the combinatorial problem of computing the permanent matrix. So if you analyze the case where L is equal to n minus 1, this is kind of an extreme case where you take all blocks with all but one side. Okay? from the point of view of the block shuffle dynamics, maybe this is not so interesting, but from the point of view of the application, I will tell you this is actually key. And what you find is that you have this subadditivity estimate. Namely, if fx just denotes the expected value of f condition on the position, on the label of the particle at x. Think of this fx. Then, if you take L equal n minus 1, you can easily translate the previous inequality, the previous theorem, into this inequality here. The sum over all x of entropy of fx is bounded above by Cn times the total entropy of f. And Cn is this quantity here, n log n over log n factorial, which if you expand, it's equal to 1 plus order of 1 over log n. This is interesting because it's known from general facts that if you're able to get a subadditivity in this inequality with constant equal 1, then your measure is a product measure. So here you're getting 1 plus something small. And so this is telling you how much your measure is not a product measure. And in some sense, it looks more and more like a product measure, right? Because of the reason I told you, the correlations are very weak when n goes to infinity. And this is a precise quantifier of this property. But more interestingly, this proves this conjecture about the permanent that was formulated by Carlin, Lieb, and Loss around 20 years ago, and also independently by Samorodnitsky in 2008. And the conjecture says the following: take an arbitrary matrix A with non-negative entries, and consider the permanent. Permanent is the sum over all permutations of the product of A, I, sigma I, where sigma is. Now, there is some interest in computing permanence for many reasons. And you may be familiar with the fact that permanent is a difficult quantity to compute, unlike determinants. For determinants, you have good algorithm. For permanent, you don't. And then it is important to obtain upper bounds on permanence in terms of simpler quantities, because this gives you some options to do efficient algorithms. And if you write Ri for the ith row of the matrix A and consider the LP norm, you can look at products of the LP norms of the rows. These are somewhat simpler quantities to consider. And what turns out to be the case is that the permanent of A is always upper bounded by the product of the LP norms of the rows for any P larger or equal 1. And the coefficient you have to put in front is essentially the coefficient that corresponds to the case where the matrix A is the identity. So one would be the case, what you have to put here when the matrix is the identity. And this n factorial over n to the power n over p is the quantity you have to put here when A is the all one matrix. So all ones everywhere. And the conjecture was that these two are actually the worst cases when you do this. For any other matrix, it's bounded just as in these two cases. And actually, the equality is uniquely achieved at this. And we could prove this theorem just by using this inequality here. And I can tell you very quickly why. This follows essentially from the Braskamp-Lieb type inequality, because by duality, this inequality here, the subadditivity, is equivalent, as I wrote before, to some Braskamp-Lieb type inequality. And this Braskamp-Lieb type inequality, you can write the left-hand side, if you choose phi x, function phi x of suitably, you will get the permanent, and here you will get the rows. So it's a simple computation. We don't need to go through the detail. But once you get this inequality with the exact coefficient here, it's not difficult to get the direction. In fact, Carl and Lieberloss were aware of the fact that if you could prove this inequality, you would get the thing, but they could not prove this. So if you want, the conjecture was to establish this. And this is what we proved with Alexandre Bristier as a corollary of this more general mean field type block decomposition of the entropy. Okay, so this is what I wanted to tell you. That's it. I guess that was it. Thank you very much.
Any questions? This is for this coupling dynamic, but I think there are other types of markers that have this type of factorizations.
Yes, actually, that's a very good point. If we are trying to understand this for other dynamics as well, here I presented only the permutation, but actually, one thing that you can observe is that usually when you have some interacting system that is represented by a Gibbs measure, say, then what you can do is heat bath dynamics. Namely, you choose with certain rates certain subsets of your variable, and you want to update them conditionally on what you see in the other variable. So it's exactly what we're doing here. And you can think of a spin system, say, Ising model. And then what you do is the simplest of these dynamics is Glauber dynamics, where you pick at every step one single side. You could do more sides, you could do large subsets of sides and so on. And what you observe is that if you write the Dirichlet form of this process, it's exactly a sum of local variances. Just like formally, nothing changes actually. And so again, you can think of the spectral gap as a functional inequality relating the total variance to local variances. And again, you can think of the entropy version of that, which will give you understanding of the relaxation to equilibrium in relative entropy. And once you have the rate of decay in relative entropy, you can do mixing times, which would be usually optimal if you use the relative entropy. And they will not be optimal if you use spectral gap. So there is some interest in computing these constants in general, not just for permutation, but in general. And there is some progress in this direction, but it's not always easy to obtain. What we have recently obtained with a PhD student in Rome is a statement of the form that if you have sufficiently weak dependence in your system, then you will have a complete factorization of entropy into blocks with a constant that is controlled by the alpha star, namely the case of independent random variable. Because alpha star is what you get when you have independent random variable from that measure. And it turns out that if you have sufficiently weak dependence, say high temperature Ising model, then you can prove the full factorization of entropy with a constant that is an absolute constant times the alpha star. So that's the type of result that you can get.
Yeah, so when you say high temperature, does it go up to the critical?
Yeah, that's a good point. In simple cases, it does, like Curie-Weiss, like infield. And also, in 2 dimension, we are able to prove for 2 dimension that up to the critical point, you have all this block factorization. In any bounded degree graph, actually, we have pretty strong results up to the so-called 3 uniqueness. You're familiar with that, but okay, having a result that really covers always the one-phase region is more delicate. But yeah.
What about Spencer-Lang dynamic?
Yeah. Okay. So we were quite happy to understand at some point that actually this technique worked well for Spencer-Lang, at least when you have a bounded degree graph. So for say two-dimensional Potts model, any using a Potts model, you can go up to critical point and prove a rapid decay of actually optimal mixing bound on the Spencer-Lang dynamic by using this block factorization. And what you use in that case is this so-called coupling. And so what you do, instead of doing block factorizations of entropy, you basically do the entropy on the spins condition on the edges, and then you do the entropy on edges condition on the spin. It's really a natural way to look at things, this factorization. Spencer-Lang is a good example where you appreciate the power of this technique.
Because that's more global.
It's more global, and this technique is designed to do arbitrary shapes, so it goes in that direction.
Any other question?
How does the proof go for the entropic version again through recursion or?
Yes, okay, good point. In fact, what we tried is to repeat the kind of recursive argument that were done for modified log subboleth. And you have to modify several things, but the core structure of the recursion is the same. So this Yao approach, martingale approach, if you're familiar with that, it turns out that this is the right way to prove this thing. You have to twist bits, but it's doable. And the good thing is that while for log subboleth, for modified log subboleth, it will not land the correct answer, here it allows you to compute the constant sharply. And as we have seen with the permanent bound, computing the constant here is crucial. It's not just it's not just a curiosity. Thanks to the exact computation of the constant, you're able to obtain something.
I mean, I just have sounds very naive. I'm not sure even it makes sense or not. Does it, we sort of say that permutation, number of numbers, is it finite always, right?
N is finite.
Yeah, so would it go to infinity? Would there be any scaling limit?
Yeah, if you look at local dynamics, you can define local dynamics in infinite volume. For Ising model, if you look at Glauber dynamics and you are in a lattice, say Z2, then you can define the infinite volume dynamics. And it's crucial that the updates are local because, but then you can actually translate these inequalities to the infinite dimensional problem, because say for Glauber dynamics, if you scale things correctly, there is no dependence on n, these bounds. So if you do things correctly, you can get a bound that is independent on the size of the box, provided you have some high temperature condition, something that guarantees that these inequalities are satisfied with some constant that is independent of the dimension. And then in that case, you can go to infinite dimension.
Are these like Dobrushin conditions?
Yeah, in ZD Ising models, you can use some special mixing condition or the Dobrushin condition. Yeah. So you need some condition because otherwise the dynamics, otherwise the inequality will hold with constants that they generate when you take a mean. But if you want constant that stay uniformly positive, then you need some weak dependence.
Any other question? No. If not, let's thank you again for
Thank
the
you.
session. There should be some tea. This was.
So what exactly are we trying?
But you studied Markov chain?
We also and there is I was really actually understand marketing.
You went to? Yeah, that was slightly fun.